Welcome to Data Skeptic. Data Skeptic brings you discussions about how data is changing our world. Our interviews are conversations with thought leaders in topics like data science, machine learning, and artificial intelligence.
Gokula Krishnan Santhanam is currently a master's student in computer science at ETH Zurich, focusing on machine learning and distributed systems. He received his bachelor's degree from PITS, Pilani, India, graduating with distinction, and has worked on a wide range of topics including IoT, intelligent vehicle systems, computer networks, as well as machine learning and AI. Previously, Gokula interned at Google Research, Georgia Tech, and the Indian Space Research Organization, working on machine learning projects. Would you mind giving a quick summary of what a GAN stands for and what it is?
Sure. A GAN stands for Generative Adversarial Network, and it actually consists of two networks. One's called a discriminator, another one's called a generator. What the generator tries to do is it takes in a random input, like a vector of random numbers, and it tries to generate realistic seeming images. And the goal of the discriminator is to distinguish whether its input is from the dataset or is it from the generator. These two networks kind of play a game. At the end, the generator has learned to generate images that look like the data distribution. So the common analogy that's used is you can imagine the discriminator being a cop and the generator being a counterfeiter, and so they are trying to best each other, and at the end the counterfeiter generates currencies that look exactly like the real one, and the cops are pretty baffled because they can't distinguish whether the input is a real one or a counterfeited money.
Yeah, I think that's a great example, in fact. There's a term your paper uses quite a bit, and I've seen it, I think, a few other places, and I think it's a very well-chosen phrase to describe a situation that's important in this area, and that's the phrase data manifold.
Mm-hmm.
Would you mind giving a short definition of what a data manifold is?
A simple way to explain it is sort of the space in which all the images exist. So let's say you have MNIST, which is just a bunch of images, right? So each image is just a matrix of ones and zeros. A manifold is basically the space that all the data points belonging to MNIST lie on. If you look at MNIST, it's a 28 cross 28 image, so that's around 784 dimensions, but it consists only of ones and zeros. So it's a subset of the 784 dimensional space. So the subset in which the data points lie in, that's what a manifold is. A data manifold is, yeah.
So when I think of MNIST, that 784 dimensions per image or pixels per image, obviously most of the images of the set of possible images are just white noise to the human eyes. We wouldn't recognize them for anything. It's sort of the ones that look like digits that wound up getting into MNIST. Is that thinking along the right idea?
Yeah, that's correct. So you're talking about the subset where you can find the data points in. Yeah, that's correct.
So GANs have been popular for a while, and we've seen a lot of papers about all the systems that are being fooled by GANs. And there have been a couple papers going the other ways, but yours was a very thorough one in exploring both your technique and the literature. Before we get, I guess, into your specific technique, could you tell me a little bit about other ways that people have considered defending against adversarial attacks?
There are several ways. One would be what's called as adversarial training. So what they do is, as part of the training data set itself, they inject adversarial samples into the data set. So let's say you have a library of 10 or 15 techniques. So what they do is they first train a classifier on the clean data set. They generate adversarial samples, augment the data set with these samples, and they train it again. So that's called adversarial training, and that makes the neural network robust. Another way was like using a GAN. So you train a GAN, something like a pix-to-pix architecture, the kind of things which is used to convert images into their semantic segmented images, things like that. So they try to train a GAN that generates adversarial samples, and they train the classifier on the augmented data set. So there are multiple ways of doing this. The literature now is more of like someone comes up with a way to defend, and the conference someone comes up with a way to break it, and so there's an adversarial game going on there as well.
Quite a cat and mouse game we have.
Yeah, indeed.
When you look at GAN, we obviously have the generator and the discriminator. Can you talk about all the actors at play and the core idea and how the Cowboy system kind of overlays those different actors in the system?
Sure. So let's start with the classifier. If you look at what the classifier is doing, it's just trying to learn a surface that discriminates between two. Let's say if you're training to discriminate between cats and dogs, so it's just learning the surface to differentiate between cats and dogs. So it has no idea about the data manifold, and what it ends up doing is it gives high confidence predictions in regions where it has never seen data points from. That's one problem with the classifiers. And what we found through empirical methods, that adversarial attacks tend to push the data points outside the manifold, and these sometimes end up in such regions where the classifier gives high scores, but it has no reason to say anything because it's never seen data points from there. What the next idea was that the discriminator of the GAN gives high scores to points inside the manifold, but it does not model the likelihood under the data distribution. But the scores of the discriminator can be used as a good proxy for belongingness. So if the discriminator score is high, that means there's a high chance of the input belonging to the manifold. If it's low, then there's a high chance of it being outside the manifold. So we can use this as an effective way to detect adversarial attacks and adversarial samples. Based on the discriminator score, you can reject samples saying that, okay, this is adversarial and I'm not going to predict it. So that's the first part of Cowboy. Most of the time, you don't want to just stop there, you want to clean it as well. If the data points are outside the manifold, you want to bring it back into the data manifold, but you should also keep it visually similar to the input, because you can bring it back to the manifold and it could happen that an image of a cat becomes an image of a dog. You don't want it. You want to keep it as visually similar as possible, but you want to bring it back into the manifold. So that's the overview of the idea, and the paper just goes on to talk about why these ideas make sense, and kind of references in literature about what other people have done in similar areas, then their experiments and results.
So there's one quote I'm going to pull from the paper that I think really helped me understand where you were going with it. It's when you say, "We postulate that adversarial samples lie outside of the data manifold and that the discriminator can effectively detect this." And I guess once you've said it, it sounds a little obvious, but I felt like it was a real keen insight I hadn't seen before. Could you talk a little bit about that realization and how that drove the project?
This was actually after a talk by Ian Goodfellow. So he had come to the Zurich office, Google Zurich office. So I had attended the talk. So the idea was that most people who use GANs for adversarial examples or for even other purposes, they kind of throw away the discriminator. But we thought about, so what does the discriminator know? It doesn't know the probability distribution, like it doesn't know, given an input, how likely a data point is supposed to be there. But what it does know is, if given an input, if it's from the data set, it's going to give it a high score, and if it's not from the data set, it's going to give a low score. That really was the key insight, that you could look, the discriminator is not completely useless. It has some information that can be exploited to both detect adversarial samples as well as defend against them. So that was the key insight. Yeah.
When it comes to then incorporating the discriminator into the prediction, what does it mean? Is it that you're taking the actual model itself and using that kind of as input to some oracle, or are we looking at the data that it generates and taking samples from it? How do we, from an implementation perspective, make use of that extra bit of information that previously no one had really used?
First, it doesn't generate any samples, so it just generates scores. In terms of implementation, let's say you have a GAN, both the generator and the discriminator, and you have a classifier. Implementing our technique into an existing pipeline takes around 10 to 15 lines of code. What these lines of code would be like is, you have an input and you try to create a new image, or you make the generator create a new image that's as visually similar to the input as well as has a high discriminator score. So you could imagine that you want to minimize the reconstruction loss as well as you want to increase the score that discriminator gives. This combination is the loss that you want to minimize or optimize rather, and that's kind of what the paper does, and that's what our technique does.
Yeah, so one of the most novel parts then is that loss function. In your mind, would it be correct to describe the key insight here as being like a new regularization technique?
I would say yes. You could look at the discriminator score as a regularization technique in some ways. Yeah.
And if you wouldn't mind, let's unpack that loss function a bit more. Just, kind of at a high level, what are some of its components and how does it differ from previous approaches?
There are two components to the loss function. First is a reconstruction loss. you have a term which is basically g of z minus x. So what this term basically says is that I want to generate an image through the generator that is as close to the input as possible. So the input is, maybe it could be a clean image, or it could be adversarially perturbed. So you want to generate an image that's as close to the input as possible, because you want it to be as visually similar as possible. You can't end up creating something that's completely different. Like if you had an input of a cat, you don't want to generate an image of a dog. So that's one term. And the second component is we want to maximize the score that the discriminator gives for the image that you generate. You both want it to be as visually similar to the input, but also have a high discriminator score, so that you ensure that it actually belongs to the manifold and it's not an adversarial image on its own. Other approaches in this area only focus on the reconstruction loss. They try doing multiple passes of this process. They have multiple instantiations. You could start with multiple Z's, and then you take that which has the best score or which has the lowest loss. So the biggest contribution is that to actually exploit the information that discriminator has.
And you name the algorithm Cowboy. Why Cowboy?
Sure. So we wanted to name it Lasso, but Lasso was already taken. So it was named Cowboy because it's kind of what's happening, right? So you had a nice data point, which it was inside the manifold, and it went rogue and became an adversarial sample. So what we're trying to do is we are trying to bring it back into the manifold. So kind of what a Cowboy does, right?
Yeah. I like that a lot.
So yeah, that was kind of the visual that I used to convince my co-author that, look, this is what we're trying to do, and it makes sense.
You also mentioned that this technique in defending against adversarial attacks is agnostic to the target classifier and its training procedure, and independent of the attack method. Tell me a little bit more about how you're able to make such a strong claim.
So if you look at the laws and as well as what we're trying to do, nowhere do we make any assumptions on what kind of adversarial samples we get or how the classifier is trained. All we know is that the classifier is a black box that takes in an input and gives a probability distribution over one of many classes, and that your input could be adversarially perturbed or it could be clean. If it's clean, then our process has nothing to do. It just says, okay, it's already inside, it has a high discriminator score, and the generator can find a noise vector that can generate this. In this way, we have made no assumption on how samples are generated or how the classifier is trained. We just assume these are black boxes and we just run on top of them. We just assume that these are kind of like APIs that you can query and get things, and that you can pass gradients through. That's about it. In that way, it works on black boxes, and that's why it's so general.
Like so many of you, I'm constantly learning for the pure pleasure of it, and that's why I love the Great Courses Plus. There's always something new to discover. The Great Courses Plus gives you unlimited access to over 10,000 fascinating lectures, presented by top professionals and experts. There's many topics to choose from, tons of math and science things, history, language, and the arts if that's your taste, even hobbies like cooking or travel. Let me tell you a little bit about the robotics course. There's 24 lectures of just about 30 minutes. The length and content are both perfect for a busy schedule. The content is very hands-on. This isn't a lecture just talking at a chalkboard. While you could enjoy this in audio form, I definitely recommend the video version for this lecture. There's a lot of great visual accompaniment, and you don't want to miss out on the full deal. As you explore topics like animal-inspired robotic design and swarm robotics, the focus is on real-world applications and implementations. Taking this course will teach you all of the principles and challenges of robotic design that you'll need, whether you want to pursue robotics or just understand this growing field. You know, robotics is a topic close to our heart at Data Skeptic, but one we really haven't covered that much. You can fill in the void in your mind with the Great Courses Plus. If robotics isn't your passion, check out any of the other great courses. There's no doubt you'll find something interesting in their vast library. I can help get you access to that library, but you gotta act now because this is a limited time offer. The Great Courses Plus is offering 1 free month of unlimited access to Data Skeptic listeners. To get that, you have to follow my instructions exactly, okay? Go to this exact domain, thegreatcoursesplus.com/data. That's the one spot to get this free month trial. We were talking about this cat and mouse game that exists in the literature Will there be a response to this, or have you kind of put a final nail in the coffin, given that it's sort of robust and independent of the actual adversarial attack style?
I think once the paper is out, there will be people trying to fool it. I was contacted by one of the other authors working in this area, like, hey, could you try this attack? People are interested, and I don't think it's the final nail in the coffin, but it's definitely one more.
Mm-hmm.
And we are getting there. So one of the biggest concerns would be that it depends on the quality of the GAN, and GANs have been shown to be notoriously difficult to train. We show that even if you have a mediocre GAN and you don't use any of the latest techniques or something like progressive GAN, just the old DC GAN that you have from, I don't know, 2014, it still works. So that's kind of one of the cool things about our paper. This works for images whenever the adversarial samples go out of the manifold. There's some recent results that show that there might be some points inside the manifold as well. That might be one drawback to this process, but all the methods that generate adversarial samples, we show that all of them push the samples outside the manifold.
There's two steps to Cowboy, if I'm not mistaken. First, there's identification of an adversarial example, and then there's the cleaning of it, from the cleaning out the adversarial noise. Could you talk a little bit more about that step?
So the first one would be just to pass, you take your input and you pass it through a discriminator and you get a score. Depending upon your use case, let's say maybe you're processing medical images and you want to be sure that your input is clean. So you could have a high threshold. So let's say if my discriminator gives a score of greater than 0.8, only then will I say the input is clean. Otherwise, it's adversarial. So in that way, you give the users a control knob to decide how sensitive their predictions are to adversarial attacks. Now, once you have detected whether it's an adversarial attack or not, you could just say, okay, if it's adversarial, I'm not going to classify it.
Mm-hmm.
But that's really bad because you don't want to end up with a service that says no prediction a lot of times.
Mm-hmm.
So you'd want to give your best shot at a guess. Maybe you could say, you could turn on a flag that, hey, I think this might be an adversarial sample. Once you detect that it's an adversarial sample, you go on to clean it. And the cleaning is what we spoke about earlier.
So that cleaning procedure, the way I'm thinking of it, tell me if you think this is a fair characterization. It's that, a lot of times before you would maybe try and improve your discriminator so that it's able to find these finer and finer distinctions that the generator's trying to close on. The cleaning step is kind of novel in that it's saying, no, wait a minute. When we find something that seems to be an attack, we're not just going to put all the burden on the discriminator to figure it out. We're actually going to try and clean it, which should push that image way outside of the data manifold. Is that a fair characterization?
It's the reverse. You want to push inside the data manifold, right? Not outside. The adversarial sample would be outside the manifold, but in the cleaning process, you want to bring it inside the manifold. You do that by finding an input to the generator such that it creates an input as close to the original image, and you kind of guide the search by using the discriminator score. So it's kind of the opposite when you want to clean. When you want to clean it, you actually want to bring it into the manifold, not just bring it inside the manifold, but you want to also bring it to a region where discriminator has high confidence that yes, this is a real image.
Okay, I see what you're saying now. Yeah, because the discriminator was trained on whatever data you had available, not the universe of all possible images. So within that space, we could say that it has expertise where it saw previous examples, but these regions that, just happen to classify one way or the other, they're open areas that there's no expertise in, right?
Of course, yeah. So that's a reason, one of the reasons that people suggest why classifiers, like neural networks, are susceptible to adversarial attacks. They say that, contrary to popular beliefs, the surfaces that these networks learn are actually very linear, because if you look at the common activations functions like ReLU, which is just a line on the positive x-axis, if you look at sigmoid or tan edge, it saturates after a while. But if you look at where they change, right, where -1 to 1, you see that they almost behave linearly. So one of the biggest hunches that people have is that the surfaces that neural networks learn are extremely linear. So instead of imagining it as a curve, you can imagine it as multiple lines stitched together. And so what happens is, classifiers tends to give high confidence to images that are way outside the manifold. For example, if a classifier is trained on images of cats and dogs, and you feed it an image of a tiger or an aeroplane, it can't say that, okay, I've never seen this. It will give its best bet of whether it's a cat or a dog. That's, you could say, a problem with the classifiers, that they have no idea about this manifold. We use the GAN because it has idea of the manifold and bring it inside, so that you could actually trust what the classifier is predicting.
I'm curious if you have any thoughts about how your procedure would perform under a multimodal setting, where there's a GAN and the generator has a couple of different sort of clever spaces within the manifold that is producing these adversarial attacks.
What do you mean in multimodal?
If it were single modal, there would be kind of like a one trick that the GAN has. It's trying to kind of give you examples that are very in one space. Like, well, take the cats versus dogs. We have at least two modes, right? Because even though we have similarities between cats and dogs, they're different objects. And even within them, they have different breeds and that sort of thing. So a very sophisticated GAN would not just be producing adversarial examples, it would independently produce adversarial cats and dogs, and maybe even different breeds of dogs. And that's, at least in my mind, an area that a clever person would go about trying to make better and better GANs. And that introduces a little bit more complexity, because now the discriminator has to learn maybe from many different styles of adversarial attacks. Do you see that as a potential problem, or how would Cowboy deal with those sorts of situations?
I think the important thing to note here is that in our method, neither the GAN nor the classifier have seen any adversarial samples to their training. They're just trained on the pure data set, the original MNIST or the original ImageNet data set. They've never seen adversarial images during their training. So they've never seen adversarial images. And going back to your questions, if you're making more nuanced adversarial examples, that shouldn't be a problem for the GAN, because it works. It's trained. It's never seen adversarial images during training, so it works even without that knowledge. So just by fine tuning the way that you get adversarial images, it's not going to change the process or the behavior.
Yeah, that's a really interesting strength of it that I did take some notice of. In certain papers that I've seen on GANs, the idea was, well, or at least very early on, people thought, let's just take those fooling images and include them as negative samples. Maybe get the classifier to learn to recognize the label we want and also the fooling label. But at least what I've seen, maybe there's been breakthroughs, but for the most part, that's a endless game. You can keep doing that forever, and there will always be new. The discriminator will change and the generator will change, but your independence from seeing the discriminative set and still getting good results kind of speaks to its robustness in that way.
Exactly. And it also speaks to its generalization qualities. Like it generalizes over multiple attacks and multiple data sets, because it's never seen an adversarial image. The only assumption that it has is that adversarial images are outside the manifold,
right,
and it'll bring it back in. That's about it.
And can you tell me a little bit about some of the performance metrics you had comparing to other procedures and on certain data sets?
We tested on datasets like MNIST, Fashion MNIST, CIFAR-10, Street View house numbers, the kind of things that you could run on a master student's salary. And we used 5 different attack methods, and all of them were taken from this library called Clever Hans. It's part of the TensorFlow repository. In each one of them, so I could give you some numbers. On MNIST, the classifier had a accuracy of 97%, and across the attacks, the accuracy on the adversarial samples was around 10%, and we were able to bring it up to 55%. So it's not yet completely there. We acknowledge that, and we say that, hey, this process works. This is something that should be looked at. And that's on MNIST. On Fashion MNIST, the ground truth was at 89%. After adversarial perturbations, the accuracy dropped down to 8%. After using the Cowboy cleaning method, we are able to bring it up to 40. CIFAR-10, ground truth was 78%. On adversarial, it was 20%, and we were able to bring it up to 50. Street View house numbers was 87% on the ground truth, 15 on adversarial samples, and after Cowboy, we were able to bring it up to 55. These didn't recover the entire loss in accuracy, but it were able to improve. And if you look at the images that we shared in the paper as well, so it was able to do selective recovery. So we one of the examples was we had an image of an aeroplane, and it was completely destroyed, that even a human cannot say that it's an aeroplane. After processing it with Cowboy, the GAN selectively recovered only the pixels corresponding to the aeroplane. The rest was still black. In a way, it kind of learned that to classify an image as an aeroplane, you just need those pixels. It doesn't care whether the background is a blue sky or a black sky. So, yeah.
Very interesting. So as the topic of GANs has been maturing over the years, I've started to think about where we might be headed and what's going on with this cat and mouse game. And one thing that occurred to me is that if we want to produce some sort of fake image or even fake audio files or fake video files, at some point, I wonder if it's not a losing battle. Like let's say you want to make a fake image of me in some compromising position or a fake audio file of me confessing to a crime. I could read a script of my voice confessing to the crime. So, the data can exist. It's somewhere in the space of all examples. And if it's done really, really well, people will say, I'm convinced that sounds like Kyle. I know his voice. I know his, tone qualities and the way he uses words. It's exactly him. And it would be, at some point, it's indistinguishable if you have a good enough algorithm. Would you agree with that? Or do you think that ultimately the discriminator can win this contest?
So if you look at the original paper, right? So at equilibrium, the generator will learn the data distribution and the discriminator will not be able to classify between real or fake. So it's kind of a losing battle on the discriminator side, I would say. But then again, training GANs, even after the research in the recent years, it's still notoriously difficult. And only now are we able to create more and more realistically looking images. So yes, that's a future we need to be wary about, but I don't see it happening soon.
Yeah, one thing I have trouble getting my head around sometimes is, like we started out, data manifold is a great way to describe this, and it's the cornerstone of the idea, I think. But beyond 3 dimensions, I can't picture a manifold. And thinking of, these 784 dimensional images, and those are small images by a lot of standards, it's this massive space. Do you think that are the algorithms we're building today really doing a great job separating it, or are they just kind of finding the hyperplane of least resistance, so to speak? Totally theoretical question. Just curious to hear your thoughts.
I think in some ways, from my experience as well, that neural networks are pretty lazy. And unless you engineer your loss function to have exactly to get the surface that you want, they'll always find the easiest way out. For examples, all those videos you see from DeepMind about their reinforcement learning things that they find shortcuts. I'm more skeptical about what neural networks are doing because, well, that's what my current work is on. So I think they are learning something of the least resistant, the hyperplane of least resistant, if you will. So I think that might be something you need to watch out for, and that's something you need to. That's something that I'm working on right now.
Yeah, I know you might not be able to talk about everything that you're working on, but I'm curious to hear where do you go next after this paper? It seems like a great contribution, and I can tell from how well it's cited that you know the field. What comes next?
So I think next would be this paper itself to make it more expansive, like trying out more different types of attacks and over multiple data sets. And the next thing that I'm focusing on right now is how to handle adversarial examples when they are sometimes in the manifold as well. So I'm trying to do these kinds of adversarial games, but without GANs, to see whether can you make your neural networks more robust by playing an adversarial game during the training as well. I can't go into more details,
Sure.
but yeah, something along. I'm more into defending against these attacks rather than creating them.
Makes sense. Obviously, Cowboy had to be implemented on your end. Is it a TensorFlow model? Is there anything people could leverage from the work you've done? And how do you go about your development and research in general?
For me, like a research cycle starts with an idea that you brainstorm on a whiteboard, and then the first thing would be to try it out on small data sets. And I use like Google's Colab for that. Afterwards, it's pure TensorFlow on small data sets. And this one, we are kind of stuck with TensorFlow because the library that we used for the attacks, Clever Hans, is built on top of TensorFlow. So we didn't have much option to try, let's say, PyTorch. And we wanted to make sure that we use the standard implementation so that later on people don't say that, oh, you created an attack which was not the right way to implement it. So yeah, we used TensorFlow for our work, and yeah, we trained on GPUs on a local cluster.
How much of this work could we call NeuroInspired? Today NIPS as a conference is very heavily driven by computational methods, but in spirit, its name came from neural information processing systems, that we should be learning about machine learning from the brain and vice versa.
Mhm.
But to my read, certain work, and Gans is one of them, it's getting disconnected from anything that's really neuro-inspired. Do you see it the same way? Is there something I'm missing?
Yeah, it's pretty. You're spot on. Like other than, for example, convolutions is one way that's neuro-inspired, but everything that we build on top, we don't make an active effort to say, how does it look when compared to biological
Mhm.
neural systems? So I don't think it's a focus. There are people in systems neuroscience who try to do this, but I don't think the mainstream machine learning community is actively doing this. If you have some idea and it works, it's kind of like icing on the cake. Like, hey, even humans or other animals do something
Yeah, yeah.
similar.
Well, I'm going to have a link to the paper in the show notes for people who want to read it, and also I'll especially encourage them to go check out the images to get a little insight into the cleaning process and whatnot. Gokula, where can people follow you online?
You can follow me on Twitter. I'm at Gok Studio. That's GOKSTUDIO on Twitter. Yeah.
Excellent. We'll have that in the show notes. Well, thank you so much for taking the time to come on today and talk about your research.
My pleasure.
Data Skeptic is a listener-supported program. To support the show, visit dataskeptic.com and click on the membership tab.